everyone. In this video, I'm going to show you how to graph rational functions. We're just going to deal with some basic rational functions and just keep it simple in this first lesson. So up here at the top of this graphic organizer, it tells you step by step how to find all these different things. So this is what we're finding, and this is how to find it. So the first thing that you always want to do when you are presented with a rational function that you're supposed to graph is go ahead and factor the top and bottom and cancel whatever can cancel. So you want to reduce your function first. So if you look at this example here, you start out with a trinomial on the top and the bottom. Both of these trinomials will factor, as you can see here. And if you notice, the x plus 4's can cancel out, so this is our new reduced function. So that's the first thing you always want to do when you're graphing rational functions. Factor, cancel, get it simplified. The second thing that you want to do is find something on the graph called a hole. Okay, it's a hole in the graph. And the reason they call it a hole in the graph is because you can see in this example here, it's where the graph's curve has a gap in it. So there's a hole in the graph. And we denote that hole in the graph by drawing an open circle there. So to find the order pair where the hole will be located is using these steps 2 and 3. We only have a hole in the graph if we cancel something when we're reducing our function. So the x-coordinate of the hole comes from this canceled factor. So as you can see here, x plus 4 was the factored cancel. And it says right here, it's the x from that canceled factor. So I'm going to rewrite this and say that we take that canceled factor and set it equal to 0. So if I take that x plus 4, I'm going to write it over here. If I take that x plus 4 and I set it equal to 0, when you solve for x, now you can see that the x-coordinate of the hole is -4. So you can see steps 2 and 3 right here. For step number 2, they found that the x-coordinate was -4. So they didn't show you how you found that, so that's why I wrote it over here. So that's where the -4 comes from. So once you have that x-coordinate, to find the y-coordinate of the hole, because remember this is an order pair, you need an x and a y-coordinate. To find the y-coordinate, we're just going to take the x value that we just found and plug it in to this reduced function here. So if we take -4 and we replace both of these x's with -4, you can see the work written out right here. It gives you 3. So the order pair of the hole is -4 and -3. And remember, you only have a hole if you cancel a factor when you're simplifying your function. So that's the steps 2 and 3, is finding the hole. There's also something called a vertical asymptote. So vertical, remember, it goes up and down. So you can see on the graph, this dotted line going up and down right here is the vertical asymptote. Remember, asymptotes are kind of boundary lines. They're lines that our graph is going to continually get closer to, but it's never going to actually touch or cross that line. So we need to know how to find them. So to find the vertical asymptote, it's super easy. It's the x from the remaining factors in the denominator. So I'm going to reword that and say take the denominator and set it equal to 0. So you just take the denominator and set it equal to 0. I tried to fit it in right there. And that's how you find that vertical asymptote. So if you take this denominator, x plus 1, and you set it equal to 0, then you can see that's where they get the x equals -1 for the vertical asymptote. All right, once you find that, the next thing are the x-intercepts. So to find the x-intercepts, it says it's the remaining factors in the numerator. So this is where you just take the numerator, or the top, and set that equal to 0. So if you take the top here of the reduced function, x minus 5, and we set that equal to 0, then you can easily see that when we solve for x, we get x equals positive 5. So if we write that as an ordered pair, that's 5, 0. So the x-intercept is going to be at 5, or 5, 0. The y-intercept, you just plug in 0 into that reduced function. So that means replace the x with the 0. So you can see the work written right here. They just put a 0 in for both of these x's in the reduced function. 0 minus 5 on top is negative 5. 0 plus 1 on the bottom is 1. Negative 5 over 1 is just negative 5. Since that's the y-intercept, the order pair is 0, negative 5. So 0, negative 5 is the y-intercept. And you can see all these points on the graph here. The hole was at negative 4, 3. So you can see that's where that open dot is, at negative 4, 3. The vertical asymptote was at negative 1. So you can see that we're crossing the x-axis at negative 1 with that dotted vertical line. The x-intercept was at 5, 0. So that's this dot here. The y-intercept was at 0, negative 5, which is this dot here. And then the last thing that we have that we need to find is the horizontal dotted line. So the horizontal asymptote. So this is a little different. So it's not just one thing. There's 3 possible solutions for this. So we need to think about the degree of the numerator and the denominator. So this just says, is x bigger in the numerator or the denominator? So this is talking about the degree, or the exponent, the largest exponent of the top and the bottom. So there are some examples at the bottom of this page. So I'm going to slide this up a little. So when you're looking at these rational functions, to determine what your horizontal asymptote is, we just said we need to look at the degree, right? Or the exponent. So if you notice here, the degree of the numerator is 2, the degree of the denominator is the 2. So if they have the same degree, then what you want to do is you want to look at the leading coefficients. So if you notice, I just drew these in. There's an understood 1 in front of both of these x squareds. So this is 1 over 1, or 1. This is where the horizontal asymptote is going to be, y equals 1. So if you have the same degree on the top and the bottom, then we have to look at the leading coefficients. So here's another example. If you notice, the degree on this x is an understood 1. The degree on this x is an understood 1. So if they have the same degree, to find the horizontal asymptote, we have to look at the leading coefficients. So the leading coefficient here is 2 over 1. Well, 2 over 1, or 2 divided by 1, is just 2. So the horizontal asymptote for this example is at y equals 2. The third example also has the same degree. Understood 1 for both of those degrees. So if you have the same degree, we look at the leading coefficients. So the leading coefficient here is 1 over 2. So that's why it's 1/2 this time. So the first 3 examples have the same degree, so that means you look at those leading coefficients. This fourth example, though, look at those degrees. The degree is 1 on top and 2 on bottom. So you can see here it says that the horizontal asymptote is at 0, y equals 0. So you need to notice that if the degree is bigger on the bottom, then that means your horizontal asymptote is always y equals 0. So if the degree is bigger on the bottom down here, then your horizontal asymptote is going to be at 0, y equals 0 every time. So that leads me to another question that I don't actually have an example of on this. What happens if the degree on the top is bigger? So if that's the case and the degree on the top is bigger, then that means there isn't a horizontal asymptote. And we're just going to start out with some more basic rational functions in this first lesson. So we're not going to actually have any that you're going to have to graph like this. I might ask you to find all the characteristics for a graph like this, but I might not actually have you graph it. So if the degree on the top is bigger, there isn't a horizontal asymptote. And we'll talk about what that means later on. But for now, you just need to know that if the degrees are the same, then you look at their leading coefficients. And if the degree on the bottom is bigger, then the horizontal asymptote is at y equals 0. So if you look back at our example up here, the degree of both of these x's is 1. So because they have the same degree, we have to look at their leading coefficients. So in front of this x, there's a 1. In front of that x, there's a 1. 1 divided by 1 is 1. So the horizontal asymptote is at y equals 1. So you can see, crossing through the y-axis at positive 1 is that asymptote. And then we just draw in our two curves, making sure we pass through the points that we have already plotted, and make sure that your graph is approaching those asymptotes, but never actually touching or crossing them. I'm not going to make you find extra points. Hopefully that was helpful and made sense. I'm going to make another video with some examples.